Hello everyone, welcome back. In this particular video, we're going to focus on the stereochemical outcome of a Wittig reaction. So the stereochemical outcome of a Wittig reaction relates to the stereochemistry of the product alkene that's formed. And I've sort of chosen an example here to walk you through through this concept. Okay, so what we're looking at here is the reaction between an aldehyde and an ylide molecule. Now, when the ylide reacts with the aldehyde, there are two possibilities for the alkene product, stereochemical possibilities here. We could either make the Z-alkene or we could make the E-alkene. Now note that in this particular example, the Z-alkene is the same as the cis and the E-alkene is the same as the trans, okay? But this could lead to confusion later, so I'm going to continue with the terminology of Z and E so that it does not become confusing in another example when we get to like a tri-substituted alkene, let's say. Okay, so like I said, there are two possibilities for the alkene product. You can either make the Z stereoisomer or you can make the E stereoisomer. And these two stereoisomers are diastereomers of each other. Now it turns out the nature of the product, okay, the stereochemical outcome of the reaction really depends on the stability of the ylide. So the ylide actually decides which of these products would be formed, what would be a major product. Now, it turns out when we have simple ylides, okay, simple ylides, and I'm going to define these as ylides which are unable to delocalize or stabilize the negative charge. Okay, so when you have simple ylides that are unable to stabilize the ylide, the negative charge on that carbon atom, then the product is a Z alkene. Okay, and this could include just simple alkyl groups. So the R group here is just another methyl group, or it could be like another carbon chain, which does not have any features to help stabilize the negative charge. Okay, that would give us the Z-alkene. The other scenario is where the ylide features an electron withdrawing group or a phenyl ring, let's say. In these cases, the ylide is stabilized, and whenever you have a stabilized ylide, you get the E-alkene as the major product as a general scenario. Okay, so examples of cases where this ylide would be stabilized, I'm going to list a couple of them here, are, let's assume that we have an ylide where we have the triphenylphosphine charge, and let's say there's an ester group right next to this ylide. Okay, so if we have an ylide like this, where this R group is now an electron withdrawing group, like an ester group, then the negative charge here can do resonance, okay, or it can be stabilized via resonance because that negative charge is now spread out over two atoms, or like a couple of atoms here, okay, because it's allylic in nature. So the negative charge is stabilized. So this would be one example where the ylide is resonance stabilized. So our product is going to be an E-alkene. Another example that you can think of is where you have a benzene ring over there. Okay, so if we had an ylide like this, where the ylide is benzylic in nature, in this particular case, again, you can see that the negative charge can be resonance stabilized, and you can write several resonance forms here. So I'm not writing all of them, but I just wanted to capture a few examples where the ylide is stabilized. So whenever the ylide is stabilized, it gives you the E-alkene as the major product. Let's go ahead and look at a few examples where simple ylides and stabilized ylides are used, and let's try to draw the products that would result from those. Okay, let's go ahead and look at a few reactions where carbonyl compounds are reacting with ylides. And I've basically put down a few variety here where we have simple ylides and we have stabilized ylides. So if you look at the first example here, we have an aldehyde that's reacting with a simple ylide. This R group here is just a methyl group. So this would be an example where our product is going to be the Z-alkene. So if I have to write the product, what's going to happen here is you're going to have the double bond between the carbonyl carbon and the ylide carbon. You have 1, 2, 3, 4 carbons. So you get 4 carbons. You have a double bond. There's the hydrogen here. And since we are writing the Z-alkene, the methyl group is going to be here, and the hydrogen is over there. Because if you look at the ylide carbon, that has 1 hydrogen on it and has a methyl group on it. So by putting the methyl group in the same side as this propyl group, I'm writing the Z-alkene here. For the same aldehyde, if we start with an ylide, which is now resonance stabilized because of this ester functional group that's present, the product that we're going to get would have the double bond H. But now the ylide carbon is connected to the carbonyl carbon, or what was the carbonyl carbon prior, and the hydrogen is going to be here. And on that end, I would have the OMe. So making the E-alkene here. Okay, so those are 2 examples with aldehydes. Let's look at 2 examples with ketones now. So we have a ketone here that's reacting with a simple ylide. No electron withdrawing groups, no stabilization of the ylide. In this particular case, our product is going to be double bond O, methyl group over there. Since we're trying to write the Z-alkene or the Z-olefin here, we will have the hydrogen over there from that ylide, and the ylide has 2 more carbons to it. So we're going to put the 2 hydrogens here. And what I've written here is the Z-alkene. Now, in case you're confused about how we're doing the E and the Z, realize what we're doing is we're assigning priorities to the groups that are attached to both of these carbon atoms that are double bonded to each other. So when I look at the carbon at the top, there is there's an ethyl group, there's a methyl group. If I were to assign priorities, this is higher priority, that's a lower priority. And this priority is assigned using the Kahn and Gold-Prelog rules that we use for assigning stereochemistry, priorities in stereochemistry. So that's 1, that's 2. And similarly for the bottom carbon, this is 1, that's 2. Since both of the higher priority groups are on the same side of the double bond, this is a Z-alkene. The same ketone, when it reacts with an ylide that is resonance stabilized or stabilized by resonance here, our product is going to be double bond with the methyl group over there. And now hydrogen goes here, and I'm going to put the phenyl ring on that side. And again, when you look at it, if you assign priorities, higher priorities, second priority, higher priority, opposite sides. So that means this is an E-alkene. Okay, so those are some examples that basically give you an idea about how you're putting down these products. So whenever a carbonyl compound reacts with an ylide, the stereochemical outcome is determined by the stability of the ylide. When you deal with a simple ylide, the product is a Z alkene. And if you're dealing with a stabilized ylide, something that bears a group that can do resonance or maybe an electron withdrawing group, then the product is an E alkene. So I hope you find these examples helpful as you study this new reaction of carbonyl compounds.